Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. In this video we will discuss the functional description, the working principle, circuit diagram of SUOER MA1230 12V 30 ampere battery charger. It is from China. It is a requested video from one of my viewer from South Africa. He sent me this circuit diagram for this battery charger and he asked me to explain schematic. He wants to know the working principle of this battery charger, especially how MOSFETs and transistors are driving. And I also received a message, can you please explain battery charger with protection 60 volt 10 ampere. So let's discuss this circuit. When we discuss any battery charger have some special sections. Input filter circuit is here, that is the first part. The second part, that is DC rail, bridge rectifier and a DC capacitor, bulk capacitor. Then we have a low voltage power supply for applying VCC for the circuit, and then we have a push-pull power supply having a pulse transformer and switching network, power transformer, rectifier section, and then we have a current and voltage control circuit which will control the charging current and charging voltage, and it will monitor the battery level, battery cutoff, everything it will monitor. And then we have a reverse polarity protection, anti-reversing protection circuit. In this portion we have current measurement circuit. This one is voltage measurement section, current measurement section, and it have a TL494 IC which will control the push-pull power supply. This diagram by engineer Munzir Salim. Here we have input 220 volt. Might be this diagram have some errors, no problem. We have to take a concept how the circuit is working. Fuse, filter circuit. Here we have NTC RT1 5D13. It is 5 ohm protection from surge currents. So this circuit will protect from over frequency, high frequency spikes and over voltage spikes, and it will protect the circuit from electromagnetic induction and everything. Then we have bridge rectifier here, 6 ampere 1000 volt diodes. These 4 diodes will make a bridge rectifier. After that we have a capacitor. It will charge at voltage applied. For example, we have applied 220 volt. 220 multiplied by 1.414 because we are using bridge rectifier, so here we will receive approximately, we can say, 330 volts. This capacitor will charge. This is primary ground. The positive voltage are reaching to Q3 drain and negative voltage to this Q4 source. We will leave these transistors here, these MOSFETs here. First we have to discuss the next circuit. Here we have R37, that is 100 ohm resistor. This 100 ohm resistor is limiting the current and it will charge this capacitor, that is 4.7 microfarad, 400 volts. And these voltage are applied to this transformer. It is flyback transformer and Viper 12A IC, that is offline switcher for flyback converter. Positive voltage are applied to primary one side and the ground side is connected to source pin. So this IC will take feedback from pin number 3 from optocoupler, and pin number 4 are VCC or VDD voltage which are provided from this auxiliary winding. When this IC will receive ground, it will take this positive voltage to drain pin, and internally it will start by startup voltage from inside the circuit, because Viper 12A have internal built-in startup resistor, startup current. It will charge this capacitor internally for soft start, and this IC will start switching. It will provide ground from source to drain to this primary. Positive voltage are already applied to primary winding, and this IC will provide ground. When this IC will start switching, there will a magnetic field in primary. So this magnetic field, varying magnetic field, will switch voltage, will generate voltage in secondary and also generate voltage in auxiliary winding. Auxiliary winding will provide voltage which will be rectified from 107 diode from 10 ohm resistor, and this voltage will provide it to VDD pin. This IC will take external auxiliary voltage from this winding, and now we will take voltage in the secondary. Here we have D13, the voltage will rectified at this capacitor charged. Here is a ripple removal capacitor. Here we have current limiting resistor for this optocoupler R42 and this capacitor for preventing from false switching. Then we have R43 and R39 R4. These two resistors will form a voltage divider network, and it will provide 2.5 volt when we will receive 15 volt in the output. So this 5K and 1K, it will make a voltage divider network. So at 15 volt it will provide 2.5 volt voltage reference at reference pin. So this IC will give a cathode current and it will switch this optocoupler LED. When this optocoupler LED will generate a light, it will cause to conduct this transistor. This transistor will switch this positive voltage which are rectified from this diode and provided from this auxiliary winding. So voltage provided, VCC or VDD voltage provided by auxiliary winding are switched through this transistor to the feedback pin. So it will signal, it will caution, it will intimation to this IC that the voltage level 15 volt are maintained at output. Anytime the voltage level is dropped, this conduction will decrease and it will change the feedback level at pin number 3. So this IC will increase its pulse width, duty cycle, it will increase the switching time, so it will cause to increase the voltage in secondary. We will take a regulated 15 volt. If the voltage are increased at that time, it will also provide a feedback so that this IC will decrease its switching. So it have to maintain 15 volt in the output. So now we receive this 15 volt. Here is a 2K bleed resistor and we have 47 microfarad capacitor, that is as output capacitor of this circuit. So we have this flyback circuit which will provide VCC voltage to perform a biasing voltage our next circuit. So we have this VCC voltage. Now take this VCC voltage and this VCC voltage are applied to this IC TL494 at this point. It is C1 pin number 8 and C2 pin number 11. 11 and pin number 8 are collector pins of the output transistors, that is inside of this IC, and these voltage are also provided to pin number 12, that is VCC pin. So VCC and collector voltage, because in TL494 we can provide collector voltage or we can provide ground to emitters and we can take output from collector. Here it is providing positive voltage to collector, so we will take output from pin number 9 and pin number 10. When this IC will take 15 volt, it will generate a 5 volt reference at pin number 14. So 5 volt reference is out and it is provided to pin number 13. When pin number 13 is programmed above than 1 volt, so this IC have to work in push-pull condition. If this pin number 13 is connected to ground, at that time it will work as a parallel operation. So now it will work in push-pull condition because 14 number pin is connected to pin number 13. So this IC, now it is ensured that this IC have to work in push-pull condition. Pin number 7 is ground, pin number 6 is RT, pin number 5 is CT, pin number 8 is dead time control. 5 and 6, these two components generating a fixed frequency option. The component at pin number 6 and 5 will set its frequency. Pin number 4 is used to maintain the dead time between two channels. Two error amplifiers. Error amplifier number 1, that is used for voltage adjustment. Error amplifier number 2, that is used for controlling the current. When we require to adjust the voltage or we require to adjust the current, this IC will adjust its pulse width to switch these transistors. Here we have a driver stage for this pulse transformer. As I discussed, this IC will work in push-pull condition. If one pin is high, pin number 9 or pin number 10, we have two pins here that are the output and these are complement to each other. If one is high, the second will low. For example, this IC started switching, pin number 9 is high. So when this pin is high, we can say 15 volt, so pin number 10 will ground. Now positive voltage are here. At that time, this diode is forward bias and it will provide positive voltage through this diode to this point, to this capacitor. Now the positive voltage are applied to this transistor, and this transistor will go in cutoff state. The negative side here, it will block this diode. It is now reverse bias. So this will provide a biasing level to this transistor. So this transistor will switch. When this will switch, it will conduct this ground level to this transistor through this collector emitter to this winding, and it will give a pulse through this capacitor. This transistor will switch. When it will switch, it will pass this ground level to this winding, and this capacitor will give a path for positive voltage switching. So it will give a pulse because this LC, so it will cause to generate a magnetic field pulse. It will generate to create a pulse. This pulse will transfer in the opposite side, secondary. We have two secondaries. One secondary is connected between this source and gate, and this secondary is connected between source and gate. So it will give a pulse to this MOSFET. It is the first condition when this line was positive and this line was negative. Now this IC will change the pulse. This line will negative and this line will positive. This positive voltage will reach to this diode and to this winding side. So the collapsing magnetic field will also add in this voltage. At that time, this negative line from pin number 9 will conduct this transistor, and we will take this pulse from this side. In one pulse, it will cause to flow the current from this side, and second time from the other side. So it will keep oscillating. Pin number 9 and 10 will trigger turn by turn, and these two transistors will apply ground from this side or from this side. We can say at first pulse this line is positive. So this pulse will reach at this MOSFET gate. This end is connected to positive. So these positive voltage will move from this point, from this MOSFET to this line, to this line, here, and here we have a transformer, and here we have a capacitor, primary ground. So positive voltage are applied to this winding this side, so it will cause to induce magnetic field, and this magnetic field will transfer in the secondary. Now the pulse will change. First it was conducting from this side, and now it is conduct from this side. This secondary will become positive, this will become negative. At one pulse this MOSFET will switch, and second pulse this MOSFET will switch. Now we can say this MOSFET will switch. When it will switch, this line is connected to ground. So this ground line will ride at the same line. First it was giving positive path, now this MOSFET is off, so this line will connect ground line. So it will provide ground line to same transformer. So this transformer collapsing magnetic field which was generated from the last pulse, it will cause to utilize the same collapsing magnetic field, and it will make a resonant circuit. These two MOSFETs will keep triggering turn by turn to the main power transformer, and this transformer will switch voltage in secondary. So secondary we have a rectifier set. It is center tape transformer. So we have a full wave rectifier here. When this line is positive, this line is negative. So when the signal will swap change, this line will provide voltage here. So this line will become negative, and the positive voltage we will take from the center taped winding. So positive voltage are reaching in the output through this fuse at this terminal. We have a capacitor here, C19, that is connected to positive terminal, or we can say it is connected to center tape winding of the transformer. And we will take rectified voltage through this D7, D8, D9 and D10 diodes, through this filter, through these current measurement resistors. These are shunt resistors, and the current will pass and it will charge this capacitor. Ampere meter that is connected in parallel of these shunt resistors. So how much current will pass through this shunt? It will cause to drop voltage across these resistors, and these dropped voltage will apply to this emitter, and it will show the amount of current, how much current will flow in the secondary. in the output section. Here we have obligatory resistors that are 2K resistors, R35, 36, 35A and 36A. So these resistors are connected in parallel to this capacitor. Here there is a small error in the diagram. So this line that is connected between drain and source, that is a mistake, that is an error in this diagram. Negative current will reach here, Q11 and Q12. It is working as a switch. Normally when the battery is connected here at positive terminal, at this negative terminal, so this positive and this negative terminal will apply a voltage divider network here, and it will cause to conduct this transistor, and this transistor will give these positive voltage that are here to this point, this is zener, and it will cause to switch these MOSFETs. Now these two MOSFETs will work as a switch. So the voltage negative line will pass through this MOSFET to the output point and through this MOSFET to the output point. It is a good working condition when the battery is connected in correct ways. If the battery will connected in reverse polarity, so this line will connect it to negative line and this line will connect it to positive line of battery. So in that case this transistor will cut off. Why? Because this line will become positive and this line will become negative. In that case this transistor will cut off. When it will, base biasing will disconnected because it will reverse biased. In that case these MOSFETs will open and this circuit will disconnected from this point. If this line is connected to negative terminal and this line is connected to positive terminal, in that case it will allow to pass the current, otherwise it will disconnect. It will stop the biasing to these Q11 and Q12. The positive voltage at this capacitor is taken to voltage sensor circuit. Here we have LM358, that is operational amplifier. Positive VCC voltage are applied to pin number 8, that is VCC pin. It is single supply operational amplifier LM358. So positive voltage are applied as well to R24, R10, R10. So 10, 10K and 4.7K. So 15 volt will divide it through these three resistors, and these resistors will give 2.5 volt reference when it have 15 volts here. So we can say it will monitor the voltage, and when the voltage are at required level, that is 15 volt, it will give non-inverting pin, that is pin number 3 of this operational amplifier, and it will give a voltage reference to pin number 3. When the output is started, these voltage are reaching to R29, R23 and R28, 100K, 10K, 7.5K. So these voltage divider network resistors 1, 2, 3 will also divide these 15 volt or 14 volt whatsoever in the out. So when it will monitor these voltage, when these two pins are equal, pin number 3 and pin number 2, at that time it will give output 0 volt at pin number 1. So pin number 3 is reference. So this IC will compare pin number 2 and 3 and it will give a resultant output at pin number 1. If the voltage, output voltage are above or below the reference, this IC will decide and it will give output at pin number 1. Pin number 3 we provided a reference, and pin number 2 will compare, that is output of the circuit. So this IC will compare this given reference with the output and it will give output at pin number 1. So let's follow pin number 1. So this pin number 1 is connected to R25, R27 and Q9. In some chargers these two resistors are concealed, these are hidden. So most of the time thermal paste is applied to these resistors to protect from temperature effect. These will give a biasing to this Q9 transistor. It will provide a ground level to this resistor and voltage reference, V reference, 5 volt reference, that is provided to 51K resistor, and here we have voltage feedback to this point. We will discuss why this pin is connected here. First we have to see the current adjustment. Here we have error amplifier EA2, pin number 16, pin number 15. We have two inputs of this amplifier, same as we discussed here. Here we are giving a fixed voltage, fixed reference at pin number 3, and we are comparing the output voltage, which is the output of the circuit, is reaching at pin number 2. So this IC will compare pin number 2 with a fixed reference, that is pin number 3. So let's come here. We have a reference that is built in 5 volt reference. When we apply voltage, it will give 5 volt. So these 5 volt are applied to this R13, R9, and the same 5 volt are applied to this R12 and R11. 10K. At this point we will take 2.5 volt at pin number 2. We give a reference at this pin. 5 volt are provided to R47 Zener diode, 10K, 16. Here we have a Zener regulator, and these voltage are provided to pin number 16 as a reference. So pin number 2 is reference for voltage, pin number 16 is reference for current. Now let's check how the voltage and current measurements are working. A shunt resistor here, set of shunt resistor. How much current will flow? This feedback will reach here at this point, and it is provided to pin number 15 through this 1 and 2 resistors. And we have a parallel path, 2K potentiometer, 51K potential resistor, 10K, and a voltage divider network here, and we have a parallel path for voltage setting. At peak voltage, at maximum voltage, how much current we need, we have to adjust this potential. This is a parallel path. One line is connected to here, and parallel voltage divider network is working here. So this is maximum current output setting, or we can say ampere, output ampere setting. How much ampere we need, we adjust from this potentiometer. How much current will flow, it will measure, it will monitor through these shunt resistors. Now check the voltage setting here. When these voltage are coming here, first one line is going to this IC left section for voltage setting, and the same, these voltage are reaching here, 1, 2 resistors, 3 resistors, and this one is output voltage setting, how much voltage we need. So this voltage reference will reach at pin number 1. We apply 2.5 volt reference. This is our requirement, that we set this circuit to 2.5 volt. So this IC will adjust its duty cycle to obtain 2.5 volt at pin number 1, that is feedback. We give a reference 2.5 volt to pin number 2. So this IC will adjust its duty cycle, its pulse width, until it have to obtain 2.5 volt feedback at pin number 1. And we can adjust the output voltage through varying this voltage setting. The same is here. Here we have B positive, B negative, B output. This is B section. This is the left one is A section, the right one is B section. That is, it is dual operational amplifier. It have two operational amplifiers inside. So here is a reference that is connected to pin number 5. We have 3 resistors for base biasing to Q5. How much current is flowing in the secondary, in the output section? This amount of current is provided to pin number 6. It will amplify it. As soon as the current will flow, it will give a pulse to Q5, and it will turn on the fan, and LED will turn on, red LED, that is power on. So fan will start, and red LED will start. This transistor will also take base biasing to this transistor, and we will take a feedback at pin number 1, current feedback at pin number 15, voltage feedback at pin number 1. So this circuit will work. When we will connect battery, because when the battery is discharged, its internal impedance is very low, so it will try to draw maximum current. So when it will try to draw maximum current, it will cause to drop voltage across these shunt resistors. So these voltage are applied to this current sensing network and also to this TL494 feedback network, and it will check that is the circuit is reached at its maximum current. When the maximum current will flow, it will cause to decrease the voltage here at this capacitor. When the voltage will decrease, this line will decrease, it will give a feedback to pin number 2. At that time it will give a feedback to this circuit that at maximum current, if the voltage level is dropped, at that time this IC will adjust its duty cycle, and same time, because at maximum current this pin will go high because current feedback is connected to pin number 6, that is inverting input. So it will give a pulse, it will give a drive to this Q13, and green LED will turn on. When green LED will turn on and our voltage feedback and current feedback will reach to this TL494, it will adjust its duty cycle and it will compensate the output voltage. When the output voltage will drop, it will cause to change the conduction level of this transistor. So this transistor will change the biasing of these MOSFETs, and these MOSFETs will cut off. When it will cut off, at that time this current will stop. When this current will stop, this capacitor will maintain its voltage level. When it will maintain, the same time the current line will decrease and it will disconnect this pulse. When it will disconnect this pulse, this LED will off. When it will off, this line will build voltage again. When it will build voltage again, it will also switch, it will turn on again this MOSFETs. So this on off output charging control and anti-reversing section will control the charging of the battery, and meanwhile these voltage and current feedbacks will cause to adjust the output pulse width of this IC, and it will control the switching to this pulse transformer. So in that way this circuit will maintain the switching of this transformer, and this circuit will working and charging will continue. And when the voltage level is full, when the battery is full, at that time this capacitor will become stable. When this is stable, there are no charging surges on this shunt resistors, so that time this line will stable. I hope so friends, this video is informative for you. If it is informative, give a thumb up. If you have any question, if you have any suggestion, please let me know in the comment box. If you have not subscribed my channel, subscribe it, and if you want to watch my videos in future, press bell icon button. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.